This is the Muscle Memory Senior Project for 2021. We are Team 11. The team members in this team are Philip Kaznowski, Catherine Wiesman, Emily Lowry, Caleb Verbrugge, Deidre Bortman, and Mason Convertini. Our project sponsor is the GVSU Biomedical Engineering Committee.
The BME committee requested a device that they can use as a demonstrative tool for their K-12 outreach events. Something that would catch young students' attention, introduce them to biomedical engineering and its real-world applications, and spark wonder in them. They wanted something that would turn collected electromyography data, also known as EMG data, from muscles into actuated motion wirelessly. No wires restricting a participant to any computer or to the device. A robotic humanoid arm was decided upon for the device. In addition, the project should be forward-thinking with an open-source software such that future Grand Valley students and faculty can improve upon it or add more functionality to the device. The device we designed and built has three main assemblies: a harness intended to be worn by a participant, the robotic limb, and a computer module.
The wireless EMG harness that we designed is comprised of a few primary components: an MSP432 microcontroller, a battery pack to power that microcontroller, and an NRF module to transmit the EMG data wirelessly to the base. The sensors themselves have an integrated LED, so as the participant flexes, as shown, the brightness of the LED will change according to how strong the participant is flexing their muscle. After the EMG readings have been transmitted to the base, this arm, with 3D printed shells to make it look more like a human arm, will move according to the strength of the EMG signals obtained from the harness. Each sensor from the harness is also individually responsible for controlling one of these 4 LEDs. Where the harder the participant flexes, the more LEDs on each ring turns on. There is an emergency stop that immediately cuts power to the servos when pressed, in case something were to happen, to ensure safety of everyone involved. There are 2 clamps that hold this entire assembly onto a table to ensure that the assembly does not move during operation or does not tip or wobble unnecessarily. As you can hear from that last clip, this device, although it does make some noise, isn't sufficiently loud to require any sort of sound deadening or any hearing protection during use.
All right, on to performance evaluation. At the time that this presentation was recorded, the project has 2 weeks left until completion. Our design will theoretically meet all of the set specifications if we keep on track. Verification testing on our completed device will still be needed to ensure that all specifications are met, but we do not expect to encounter issues in this process. The limb is capable of moving much faster than needed, with no signs of mechanical overloading or running low on supplied power during maximum loading. The motion as it stands when being fully operated from EMG readings is choppy, with residual vibrations lasting for a few seconds after hard acceleration or deceleration. We will be attempting to address this in the next couple of weeks.
Future works. Possibilities for future work include adding mechanical damping to the motion of the limb to reduce residual vibrations that cannot be accounted for in software. Another opportunity for future change is adding attachments to the end of the limb. Adding an aesthetic cover for the whole limb assembly to hide more of the wiring and internal components would likely make the product look even more finished and professional. Something to reduce some of the servo noise would also be beneficial in creating a more finished feel to the product. A projected display for the current position of the limb and a less technical display of the current EMG readings would make the product easier to understand for non-technical audiences and would possibly have more of an impact on the viewer. A computer-based control system would also be beneficial as a manual control mode to have more precise control of the limb.